Have you ever wondered how physicists determine the moment of inertia of a real object swinging like a pendulum? In the previous video, we used a graph to figure it out. But what if you could measure it without drawing a single graph? In this video, I'll show you two practical methods that allow you to determine the moment of inertia of a physical pendulum, using only a few measurements and some careful timing. These techniques are simple, precise, and perfect for real experiments. Let's dive in and see how it works. Again, we will start from this relation for the period t of a physical pendulum, where ICM is the moment of inertia of the pendulum with respect to the axis of rotation passing through its center of mass, and a is the distance of the currently used axis of rotation from the pendulum's center of mass. M is the mass of the physical pendulum, and g is the effective gravitational acceleration in the vicinity of the pendulum. Let's rearrange it to express the moment of inertia, ICM, of the pendulum with respect to the axis of rotation passing through its center of mass, which is what we want to determine. Of course, once we have this moment of inertia, ICM, we can then easily determine the moment of inertia of the pendulum with respect to another axis of rotation using the parallel axis theorem. Therefore, we can see that we need to measure the period of oscillation of the pendulum, t, for the chosen axis of rotation, the distance, a, of this axis of rotation from the center of mass of the pendulum, m, and the mass of the pendulum, m. This time, however, we must also know the value of the effective gravitational acceleration at the location of the pendulum. But if we know on which celestial body we are located, that is not a problem. For example, on Earth, the acceleration due to gravity is approximately 9.81 meters per second squared. More precisely, the value of the effective gravitational acceleration depends on the location on Earth and can be easily found on the internet with high accuracy. The mass appears in the equation to the first power, so it can be measured using a less precise scale. The distance, a, of the axis of rotation from the center of mass of the pendulum appears in the equation squared, so it must be measured more precisely. For example, with a vernier caliper that has 50 divisions on the secondary scale, giving it an accuracy of 0.02 millimeters. If you don't know how to measure with a vernier caliper, you can watch my video titled How to Read a Vernier Caliper, 0.02 millimeters. Accuracy explained. The holes in this pendulum are arranged symmetrically about its center, so the center of mass of the pendulum is located at the center of the middle hole. My advice is to first measure precisely the distance from the top of the hole representing the chosen axis of rotation to the bottom of the middle hole, and then subtract half of the diameter of the middle hole from this distance. Finally, in the equation, we also have the period of oscillation t of the pendulum for the chosen axis of rotation, which appears squared as well. Terms with higher powers contribute more to the overall measurement uncertainty than terms with lower powers. Therefore, the period must also be measured as precisely as possible. It is sufficient to use a stopwatch with a precision of 1/100th of a second. To further reduce the uncertainty in measuring time, we will measure not just one period, but 10 periods at once, and we will repeat this 10 times. Again, we must keep in mind that we need to measure small oscillations with a maximum angular displacement of about 5 degrees, so that the approximation holds that the sine of the displaced angle is approximately equal to the angle itself in radians. This approximation was used when deriving the equation for the period of a physical pendulum that we started from. We repeat this measurement of 10 periods of oscillation 10 times. In this way, we have measured all the directly measured quantities needed to calculate the indirectly measured quantity, ICM. Now let's move on to the second method of measuring the moment of inertia of the same physical pendulum with respect to the axis of rotation passing through its center of mass. The second method is based on using torsional oscillations of a torsional pendulum. In our case, I will use a torsional pendulum constructed from a steel wire and 1 or 2 discs. If the torsional pendulum consists of a single solid disk, then its period of oscillation, T1, is given by the following relation, where ISCM is the moment of inertia of the solid disk with respect to the axis of rotation passing through the disk's center of mass. And kappa is the torsional constant or directional moment of this torsional pendulum. The torsional constant, kappa, is a property of the wire, and in our case, its value is given by the following relation, where three properties of the wire appear. G is the shear modulus, R is the radius of the wire's cross-section, and L is the length of the wire. If we add our previously used perforated disc with 3 holes to the solid disc, the moments of inertia of both with respect to their common axis of rotation passing through their centers of mass add together. The resulting period of oscillation, T2, of the newly formed torsion pendulum is then given by this relation, where ICM is the moment of inertia of the perforated disc with respect to the axis of rotation passing through its center of mass, which is the quantity we want to determine. The moment of inertia of the solid disc, IFCM, can be easily calculated using the well-known relation, 1/8 of the product of its mass and the square of its diameter. The torsional constant, kappa, is the same in both equations for the period of oscillation, so we can use them to express ICM. Thus, we obtain this final relation for ICM. To calculate ICM, we therefore need to measure the mass of the solid disk, m, the diameter of the solid disk, d, the period of oscillation of the torsional pendulum with the solid disk, T1, and the period of oscillation of the torsional pendulum with both disks placed symmetrically on top of each other, T2. Let's now show how to measure both periods of oscillation, T1 with only the solid disk, and T2 with the pair consisting of the solid disk and our perforated disk. For torsional oscillations, the angular displacements can be much larger than 5 degrees. The initial angular displacement can be up to 180 degrees. I used an initial displacement of about 140 degrees. This angular displacement gradually decreases due to friction, but that does not affect the measurement of the period very much. As the angular displacement becomes smaller, the angular velocity also decreases, so the period of oscillation remains approximately the same in repeated measurements. Again, to reduce the final measurement uncertainty, we will measure 10 oscillations at once, and we will repeat this measurement 10 times for both periods, T1 and T2. After obtaining 10 times the arithmetic mean, we will of course divide it by 10 to obtain the single arithmetic mean value of each period. Also, take into account your reaction time, which affects both starting and stopping the stopwatch. For an average person, the reaction time is around 0.2 seconds. Two people sitting next to each other can easily measure the sum of their reaction times, approximately twice the reaction time of each of them. The first person starts the stopwatch so that the second person can see it, but the second person must not know in advance when it will happen. As soon as the second person notices that the first person's stopwatch has started running, they shout, "Stop," and the first person stops it. The first person's stopwatch will then show the sum of their reaction times. From the equation for the period of oscillation, T1, of the torsion pendulum with one solid disk, we can also determine the shear modulus G of the wire used. To do this, we only need to additionally measure the diameter of the wire, d, and the length of the wire, l. If you found this video helpful, don't forget to like it and subscribe to our channel. Your support helps me create more quality content. Thanks for watching, and I'll see you in the next video.